Hello friends, welcome. Today we would be solving some questions, discussing some techniques on solving questions for fast and slow clocks. So as we have already discussed so far, we have covered a single clock and we have discussed formulas and techniques of finding things like angle between the clocks, number of coincidences and such. These kind of questions do not involve an accurate clock, but instead they involve clocks which are either slow or fast. So before we start solving these questions, let's first understand what are fast and slow clocks. So a fast clock runs at a speed greater than a normal clock, an accurate clock. That is, it covers a larger angle in a same amount of time. On the other hand, a slow clock covers a smaller angle in the same amount of time when compared to a normal clock or an accurate clock. A fast clock always gains time, which means that it would try to, given even enough sufficient time, it would try to get ahead of the accurate clock. Similarly, a slow clock would tend to lag behind an accurate clock. So this terminology is so important that I would like to again go through this using an example. A clock is running, like we already understand this, a clock is running if it is ticking, if it's showing time. Now again, going back to fast and slow clock, for example, let's say that if the hands of a clock take 59 minutes, so instead of taking 60 minutes that the normal clock does to cover an hour, to cover an angle equivalent to an hour, this particular clock only takes 59 minutes. Therefore, this clock is said to be faster. It is running faster, right? That's why it took less time to cover the same angle. For example, if let's say that I set a clock, right? I had two clocks, I set both of them at 12 o'clock, right? And now this clock, the inaccurate one, right? It shows 5 o'clock when we know that current time is 4:59. Right? So the current time is 4:59. The current clock, the accurate clock, is lagging behind, but this clock ran ahead and is showing 5 o'clock. Therefore, it has gained 1 minute over the regular clock. So it has gained 1 minute. So instead of showing 4:59, it is showing 5 o'clock. Similarly, a slower clock would take a longer time to cover an angle equivalent to 1 hour. And if we take our similar example, if we extend this, if it is known that the current time in an accurate clock is 5:01 and our incorrect clock, our slow clock, is showing only 5 o'clock, we know that this clock, this slow clock, has lost an hour, a minute over the accurate clock. So now, once we are clear on the terminology, I would like to emphasize that these questions on fast and slow clocks are very simple. We'll go through several of those examples and you'll see, and you should never miss these. So you should always attempt questions on fast and slow clocks. They are very simple and you'll get them easily. So now here is the first example. It says that we have a clock which starts from behind. So it is behind it has lost a certain amount of time over a normal clock. So it starts from behind, but over certain duration it has gained and now it has come out to be ahead of the normal clock. So what is the total time it has gained from being 5 minutes behind to being 5 minutes and 48 seconds ahead, which means the total time that it has gained is 54 by 5 minutes. Right? Notice I have converted these seconds also to minutes. Now this gain has happened in how much time? What is the duration from this Sunday to subsequent Sunday? Notice that the examiner is trying to trick the student here. We are starting from morning of Sunday and here we are ending on Sunday evening. So there is a 12-hour thing here. So total duration is 24 into 7 plus the 12-hour duration. This comes out to be 180 hours. Now what are we being asked? We are being asked that we are being asked that from this Sunday to subsequent Sunday, here we were 5 minutes behind and here we were plus 5 minutes 48 seconds ahead. From here to here, was there a time, there must definitely be a time when this clock would have been accurate, which means that it would have shown the exact time that an accurate clock would have shown. The difference between the times would have been 0, and we are asked to find when would that happen. When would be the time, at what time this clock would become exactly accurate. That's what we are going to find. How are we going to find that? We know that this clock started out 5 minutes behind. So as soon as this clock gained 5 minutes, we know that it would show accurate time. How long would it take to gain 5 minutes? Can we find that out? Of course, it is very simple. We know that we can do that using the unitary method. So let's apply that. So 54 by 5 minutes to cover this much time, the clock takes 180 hours. To cover 1 minute, the clock would take 180 into 5 divided by 54 hours. Right? You should always keep units here. Right? You should always keep it. Don't get confused. And this is all in minutes. And to cover 5 minutes, how much would the clock take? 180 into 5 divided by 54. If you solve it, you will get 250 by 3 hours, and this translates to 3 days, 11 hours and 20 seconds. So sometime on Wednesday, the clock would show exactly accurate time, and the time would be 8 plus 11, 20, which means 19-20 hours. Very simple question. The only thing you should note here is that we are given only one clock here, but instead we really have two clocks. The one other clock is the accurate clock against which we are comparing everything. So the accurate clock, although not mentioned in the question, is always there. You should keep that in your mind. Okay. So moving on, this is the next question. Again, we are only given the inaccurate clock here. We are only being told that there is a clock which is gaining 10 minutes. But of course, it is gaining 10 minutes with respect to what? With respect to the accurate clock, and that is always there, implied in the question, and you should keep that in mind. Don't get confused. Okay. Draw if you want to draw a diagram, and draw a diagram with two clocks. There is one which is inaccurate, and of course there is one with one which is accurate. So again, this clock is taking 10 minutes to gain, it is taking 24 hours to gain 10 minutes. Therefore, in 24 hours, the clock really covers 1440, which is of course 24 into 60. This is the number of minutes, plus 10 minutes. This is all in minutes. When it should have covered really how much? It should have covered only this much. So this is the time in 24 hours, time in minutes in 24 hours, 24 into 60, which an accurate clock would have covered. But our clock, our inaccurate clock, really covers 1440 plus 10 minutes. This is what the first part of the question is saying. Now we are being asked that from this 8 a.m. to 1 p.m. of the subsequent day, how much, if the clock is showing 1 p.m., what would the accurate clock be showing? Right? So if this clock has covered how many hours from here to here? This clock has covered 29 hours. Now what the question is really asking us, that if this inaccurate clock has covered 29 hours, an accurate clock would have covered how many hours? Can we find that out? Yes, of course. Again, unitary method comes to our rescue. This is 1450 minutes. Right? When this clock covers 1450 minutes, we know that an accurate clock would have covered only 1440 minutes. When this clock covers 1 minute, an accurate clock would have covered 1440 divided by 1450 minutes. Right? And then if you do the same thing for 29 hours, if this clock has covered 29 hours, our accurate clock would have covered into 29 into 60 minutes. If you calculate this, if you simplify this will come out to be 1680 minutes, which really simplifies to 28 hours and 48 seconds. What does that mean? It means that instead of covering 29 hours, our accurate clock has only covered 28 minutes 48 seconds. And what time would it show? The accurate clock would show 12:48. So instead of showing 1, the accurate clock would be slightly behind and it would show 12:48. Very simple. Now here is another question. These kind of questions are also being asked. In this, you have to realize that we are not given the time gained or lost by the clock. So in a previous question, we were directly given that the clock was losing 10 minutes in 24 hours, something like that, right? Here, instead of giving that per hour or per day how much the clock is gaining or losing, we are really being told what the clock is gaining or losing per intersection, right? Per coincidence, right? I'll explain that to you in 1 second. So we know that hands of a clock intersect after every so much time. We discussed this in the last class. They coincide after every so much time. What is that time? There are a total of 11 coincidences, 11 intersections in 12 hours. So this is the duration between each intersection, 12 by 11. And of course this is in hours, so we can convert into 60. So roughly in this, roughly this translates to 65 minutes and some seconds. So roughly after every 65 minutes, an accurate clock the hands of the accurate clock would intersect. We know that. For this clock, the intersections happen, instead of happening 65 in some minutes, the intersections are happening every 64 minutes. So this clock is fast. The position of the intersection is not changing. It is the same for both the clocks, for this clock and the accurate clock. But of course, this clock is reaching the intersection point faster in only 64 minutes. So how much inaccuracy is accrued? How much inaccuracy happens in one such intersection? This is the amount of time that a normal clock would take to reach from here to here. This is the amount of time that our special clock is taking. So this much inaccuracy is happening per intersection. How many intersections are there in? We are being asked per day. How many intersections are happening per day? We know is 22, which is 11 into 2. Now this is inaccuracy per intersection. We multiply by 22. This is the amount of inaccuracy introduced per day. This is the answer. You can simplify it. You can, right? So 11 you take inside. Don't divide. Don't start dividing here. First take 11 inside. This will become 12 into 60 minus 64 into 11, and 2 is still outside. I just took 11 inside. Okay, so 2 I kept outside. So notice that I have changed this divide, which I don't like. We don't like divides at all, to multiply. Right? So you should use these small techniques. They'll save you a lot of time. And once you simplify this will come out to be 16 into 2, and this becomes 32 minutes. This is in minutes. Okay, that's the answer. Moving on. Here we come to a very interesting question. This question is very simple for students, would be very simple for students who tuned into our last class. And as long as you are not cramming the formulas but really understanding what's happening behind the formulas, you will be able to solve such questions. And keep this in mind, examiners are increasingly looking for such things, increasingly looking for such questions which people cannot solve simply by cramming. They really want to understand how much you know, right? What's your real mental ability. So this question is saying that we are on a different planet, and of course we have a different system of measuring time on that planet, and that planet happens to be Mars. So in 1 day of Mars there are 36 hours. In 1 hour there are 120 minutes. Not only that, a Martian clock, instead of having 360 degrees around a circle, this Martian clock has 720 degrees around the circle, which means their circle is also really different, or of course their degree measure is really different. So now can we find out what would be the angle between the hands at this time? If you know that this is our clock, so we'll just ignore these markings for a second, but of course we know that similar to our clock, the Martian clocks would also have angles. I mean, that much we can understand. And this question is asking us to find that angle. So we can start doing that very simply. First, let's take the hour hand. So what can we say about the hour hand? Hour hand covers a certain angle in 1 hour. What is that angle? The entire 720 degrees are covered in how much time? A Martian day has 36 hours. So therefore, this entire angle 720 degrees, this entire circle is covered in 36 hours, or the speed becomes 20 degrees per hour. What is the speed per minute? Notice we are still on hour hand. Okay. What is the speed of the hour hand per minute? Per Martian minute? 20 degrees per hour really means 20 divided by 120 degrees per minute, which is equal to 1 by 6 degrees per minute. So this is the speed of the Martian hour hand. What about Martian minute hand? What can we say about its speed? A Martian day has 120, a Martian hour has 120 minutes, and these are covered in this 720 degrees are covered in 120 minutes. Therefore, the speed of Martian minute hand is 6 degrees per minute. Now we know the speed of both the hands. Can we find out the angle for both the hands? We can. What's the angle for the hour hand? It is 9 full hours. The angle would have moved, the hour hand would have moved 90 into 20. But of course, in 48 minutes, this hour hand would have moved somewhat more. How much more would it have moved? 48 divided by 6. Right? So it moves 1 by 6 degree in 1 minute. In 48 minutes, it would have moved 48 into 1 by 6, which is 48 by 6. What about minute hand? How much would it have moved in 48 minutes? It starts from 0, and then for 48 minutes it has been ticking. So how much would it move? 6 into 48. So this is the angle of the angle from 12 o'clock, of course. I mean our 12 o'clock, angle from this vertical, of course. So this is the angle of the hour hand. This is the angle of the minute hand. If we subtract those two, we will get the angle between the two hands. If you solve it, this will come out to be, and of course we are interested only in the absolute value, only in the difference and not the sign. This would come out to be 188 minus 288, and this comes out to be 100 Martian degrees. Martian degrees. Moving on, this is another question, another type of question, and it is extremely simple question if you understand one concept. There is just one concept you have to understand. You can call it shortcut trick if you will, but of course it's a concept. If you understand it, you can solve this question in 1 second. The concept is the following. If you take face of a clock, and the clock is showing certain time, let's say 6 o'clock. Right? Now this is the face of our clock. Now you come in and you start rotating, right? There is an adjustment thing behind the clock which you can rotate, adjustment dial. So if you start rotating that, the hands of the clock would move. If you rotate the clock, the hands by how much, that you wouldn't be able to distinguish between this time and the rotated time. If you rotate the clock, these hands by 12 hours, you would not be able to distinguish between this time and the new time. The hands of the clock would again come back to the same position. So these two faces are exactly equivalent. After 12 hours, no distinguishing can happen. So there is a clock which is running behind or running ahead. It is 2 minutes per hour faster. So in 1 hour it gains 2 minutes. How much would it have to gain so that we cannot distinguish between this clock and the correct clock? 12 hours, correct, right? So as soon as it gains 12 hours, the face of our inaccurate clock and the accurate clock would look exactly the same, that is, it would show the correct time. Now let's start solving the question. We can solve it very simply using unitary methods. So 2 minutes are gained in 1 hour, 1 minute is gained in half hour, and therefore a total of 12 hours would be gained in. So I have converted the 12 hour to minute here, if you didn't notice that, which is equal to 360 hours. A total of these many minutes would be covered in 360 hours. Of course, this is true for an analog clock, because the hands of the clock come to same position after 12 hours. What about a digital clock? A digital clock would show the same time after, not after 12 hours, but after 24 hours. So for a digital clock, this number would become 720 hours. And the question would of course tell you which clock to use. Moving on, this is the next question, and here again the question and the technique remains the same, but instead of having one clock, now we are being asked to compare two inaccurate clocks. So we don't have one inaccurate clock but two inaccurate clocks. One of them is running 5 minutes fast, another one is running 5 minutes slow. So how can we find this out? Again, the technique is really simple. The two clocks would show they start from the same time. When the difference between the times of those two clocks become 12 hours, they will again show the same time. So the total amount of difference in time which is created between the two clocks is 10 minutes in 1 hour. So when this difference increases, it becomes 12 hours. The clocks again would show the same time. And when would it become 12 hours? So 1 minute of difference is created in 1 by 10 hours. Again, let's take an analog clock. 12 into 60, which is equal to 720 minutes of difference would be created in 720 by 10 hours or 72 hours. Of course, for a digital clock, this 72 would become 144. Moving on, we have a clock which loses not 1, not 10, but 20 minutes every hour. So it loses 20 minutes every hour. It is now showing 4 am. So it is now at 4 am. We know that. So let me draw a clock here. So this is showing 4 am, and at 4 am it is stopped, right? It actually stopped. We set it at midnight. It is showing 4 am, and at that time it is stopped. When we, of course, since it is stopped at that time, it is not running anymore, and it will always show 4 am from then onwards. And this stopping really happened 4 hours ago. That is what this question is telling us. So it started from 12. It kept on running till 4 am, but when we looked at it again after 4 hours, right? After 4 hours, it was still showing 4 am. 4 hours have passed since it's stopping and our looking at it. So now we are being asked, what is the real time now? What is the time, real time when we looked at that clock and we saw that it is stopped 4 am. So when this clock reached from 12 o'clock to 4, how much time really elapsed? How much time really elapsed, right? This is the slow clock. So when our clock covers 40 minutes, the real clock covers 60 minutes. Note that it is slow by 20 minutes per hour. So when our clock covers 40 minutes, the real clock covers 60 minutes. When our clock covers 1 minute, the real clock covers 60 by 40 minutes. And of course, when our clock covers 4 hours, the real clock covers 60 by 40 into 4 into 60, which really becomes 36. Sorry. this should be 60, 360 minutes or 6 hours. So our real clock, our correct clock would have moved from 12 to 4. It would have moved, when this clock moves from 12 to 4, our real clock would have moved from 12 to 6. And of course, since this clock is stopped, 4 hours have passed. So from the 6, 4 hours have really passed, and that those 4 hours are accurate. And hence the time right now is 6 plus 4, which is equal to 10 a.m. That's the answer. So again, very simple. As I said, the maths is very simple. It was very simple. It took us very less time to cover 7 questions. Actually, we covered 7 questions. So it was not too bad at all, and you should definitely attempt these questions, but keep the few concepts we discussed in this class in your mind and you will come out acing. In the subsequent class, I plan to discuss all the speed related problems. They are very important for all aptitude exams. We will discuss relative speed, trains, boards and all the fun stuff. So stay tuned and don't be surprised if one of these questions comes in your exams. Thank you.